Hello guys, how you doing? Today is the fourth session of chapter 3 of Fluid Mechanics 1 with subject of physical interpretation. Follow me with the whole video. So, as I already told you, the subject of this session is physical interpretation from section 3.4, chapter 3 of Fluid Mechanics 4. Before going on instruction, I'm going to introduce myself. My name is Amir Reza Talaqat, and my email address is amirreza@gmail.com. You can always ask me your questions in the Gmail or the comment of this video. Please don't hesitate. I try my best to give you the answer as soon as possible. So, today we are gonna somehow comprehend and get the result of the two previous sessions. As you have already know, we have discussed about the Bernoulli equation along a streamline as well as a cross streamline. We are having equations 3.13 and 3.13, which are along the streamline as well as the cross streamline correspondingly. The concept of this session is that we go through the interpreting of Bernoulli equation. You know, guys, in the real world, we cannot just make easy assumptions about the Bernoulli equation, such as incompressible, not steady flow, neglecting the viscous effects or surface tension. In real world, these things are not existing actually. But however, these assumptions have really helped scientists to develop more complex theories. We are just having the pressure and the gravity in the Bernoulli equation. Nevertheless, there's an alternative procedure through which we can obtain the Bernoulli equation, which is corresponding to work and energy principle. For the work and energy principle, which is often used in the study of dynamics. In general, when we are studying the equations of the motion, it's a similar thing that we conducted in the section 3.2, which was the F equal to ma along a streamline. But for the work and energy principle, we have to make some assumptions, which are the work done on a particle by all forces on a particle is equal to the change of the kinetic energy. As you know, the Bernoulli equation itself is the equation that states both gravity as well as the pressure forces that are doing the work on the particle. As you know, the work is stated as force happening in the direction. So we are having three terms in Bernoulli equation. First of all, the pressure gradient, elevation gradient, Gz or gamma z, and the third one is half of rho v to power 2. Gamma z and p are representing the work done by weight as well as the pressure forces. And the kinetic energy is regarded as half a 1 over 2 rho v to power 2. We can just easily extract the Bernoulli equation from first and second laws of thermodynamics. This term is going to be illustrated in detail in the thermodynamic course. But here we are just naming it, which is in the term of energy as well as the entropy equations. If we do apply appropriate restrictions, we can just easily reduce the general energy equation to the Bernoulli one. the basics of this procedure are going to be demonstrated in the section 4.5 of chapter 5. So alternatively, we can just reduce the Bernoulli equation in this type, which is P over gamma plus V to power 2 over D over 2G plus Z is equal to a constant along a streamline. All of the three terms in this Bernoulli equation are labeled as units of energy per weight, which is LF over F. P over gamma is representing the pressure head, V to power 2. V to power 2 over 2G is representing the velocity head, and Z is called the elevation head. The pressure head is the height of a column of the float that is needed to produce the pressure P. Again, the height of a column in which the fluid is going to produce the pressure P. The velocity head is the vertical distance needed for the fluid to be falling and producing velocity V. Again, velocity head is the vertical distance required for the particle to be heading down and introducing or producing the velocity V. The sum of pressure head, velocity head, and the elevation head is constant along a stream line. As you already know, we have just divided the Bernoulli equation here by specific way to have it as a general form. We are having two examples, which are examples 3.4, which is about kinetic potential and pressure energy, and example 3.5, pressure variation in a flowing stream. I'm going to solve both of them in a written text for you. So just follow me with the written texts. Welcome guys to this part, which is problem solving of example 3.4, titled as kinetic potential and pressure energy from section 3.4 of chapter 3. The question is, consider the flow of water from the syringe shown in figure E3.4a. As indicated in figure E3.4b, a force F applied to the plunger will produce a pressure greater than the atmospheric one at point 1 within the syringe. The water flows from the needle, point 2, with a relatively high velocity and coasts up to point 3 at the top of the trajectory. Discuss the energy. The question wants us to discuss the energy of the fluid at point 1, 2, 3 by using the Bernoulli equation. As you know, guys, we want to talk about the Bernoulli equation. So we have to assume we are having steady, inviscid, incompressible flow along streamline, which is gonna be demonstrated as equation 3.13 as P plus 1 over 2 rho V to power 2 plus gamma Z is constant along streamline. This equation indicates that the sum of the three types of energy, which are kinetic, potential, and the pressure, or referring them as heads of pressure, heads of height, and velocity, are remaining constant by combining each other along streamline. The same concept is indicated in the table already, but in order to describe it, any change between these three factors causes the change on another ones. The consideration could be as this. Between point 1 and 2, the pressure gradient causes an acceleration. To eject the water from the needle, as you see, the pressure goes up at the high pace and velocity. Further, gravity acting on the particle between point 2 and 3 produces deceleration. Gravity, gamma z, deceleration. It causes the water to come to a monometry stop at the top of its flight. The change of energy between this is happening by kinetic energy. So, welcome guys to the last problem solving of section 3.5, which is example 3.5 about pressure variation in a flowing stream of section 3.5 chapter 3. The question wants us to describe the pressure variation between points 1 and 2, 3 and 4. The total question is, water flows in a curved undulating water slide as shown in figure E 3.5a. As an assumption to this flow, consider the inviscid incompressible steady flow as shown in figure E3.5b. From section A to B, streamlines are straight, while C to D are curved. So, let's write it down. We're having steady, inviscid, incompressible flow along a streamline. So, can use the equation 3.14, which is P plus integration of V to power 2 over R dr plus gamma z. As we are having the R as infinity, this term is going to be omitted already. So we are having it as P plus gamma z is constant. We're going to write it down between points 1 to 2. P1 plus gamma z1 is equal to P2 plus gamma z2. P2 is gauge 1, P gauge. It's going to be 0. Z1 is 0 and Z2 is H2 between 2 and 1. Yeah. So we are not considering the 0 here. We're going to apply it somewhere else. P1 is equal to P2 plus gamma Z2 minus Z1, which is H2 to 1. Note that since the radius of curvature of streamline is infinite, the pressure variation in the vertical direction is the same as if the fluid were stationary. So we're going to apply it once again here. For points 3 to 4, we're going to apply it once again here. P4 plus rho, excuse me, there's a rho over here, rho multiplied by integration of what? Yeah, Z3 to Z4. V to power 2 over R minus dz plus gamma Z4 is equal to P3 plus gamma Z3. As same as P2, P4 is also the gauge. P gauge is equal to 0. Z4 minus Z3 is H4 to 3. So we're going to have P3 as gamma H4 to 3, which is Z4 minus Z3 minus rho integration of Z3, Z4, V to power 2 over R dz. To evaluate the integral, we must know the variation of V and R, as I told you in the instruction, with the variation of V and R with Z. Even without this detailed information, we note that the integral has a positive value, as you see here. Thus, the pressure at point 3 is less than the hydrostatic value, as much as this. By an amount equal to rho integration of Z3 to Z4 V to power 2 over R dz. This lower pressure caused the curved streamline necessary to accelerate the fluid around the curved path. So this pressure difference caused the acceleration along the curved path. Excuse me, I just have to write it down and bring it up. I just tell you once again, we applied everything based on the equation 3.14 here. We have written it. We have infinite curvature, so it's going to be omitted. P plus gamma z is constant along streamline. We wrote it down between points 1 to 2. And extract the P1 from P2, which is P1 is equal to P2 plus gamma Z2 minus Z1, which is H2 to 1. Between points 3 and 4, we're going to apply it again, but we have minus dz over here, but we shall be aware that P4 is P gauge, as same as P2, and Z4 minus Z3 is H4 to 3. Doing the calculation and integration, we're going to have this pressure difference, which is by amount of hydrostatic pressure of gamma H4 to 3, by amount and by an amount equal to rho integration of Z3 to Z4 V to power 2 R dz. This pressure difference causes the acceleration along the curved path. So guys, this is the end of this session. I hope you all have grasped the fundamentals that I demonstrated to you in this session, and I'm really happy that you have accompanied me to this moment of this video. Please don't hesitate to ask me your questions about fluid mechanics or any other sections of fluid mechanics in email or comment of this video. And most importantly, please subscribe to the channel in order to get the notifications of following upcoming videos. I bid you all farewell. See you in the next session.